There are certain rules in probability which can help you forecast the chance of an event happening. And the first one is the complement rule. And it's basically that the probability of a complement happening is always equal to 1 minus the probability of the event. So let's say right here that you had outcome A was your chance of happening right here. Well, you know that the entire size of your sample has to be the full 1 or 100% of the sample size. So whatever the probability of A happening, 1 minus that number has to be the probability of it not happening. Expressed in numbers over here, let's say that we have a female open house to a gym, and we're hoping that people purchase a membership. Historically, we've looked at this and we said that there's a 37% chance of any female person that comes into the gym buying a membership. Well, what would be the complement of that? There's only two outcomes right here. It's binary. They either do or they don't. So if there's a 37% chance of a female purchasing a membership, then that means there has to be a 63% chance of it not happening. Since this is the only two outcomes, they have to add up to the full 1 or 100%. So for the complement rule, if you know the probability of one event happening, the 100% minus that probability has to be the probability of it not happening. The addition rule is used to find the probability of the union of two events. So in this case, with our Venn diagram, we're looking for the probability of A or B happening. Now, some portion of that A might only happen, some portion of that B might only happen, and some portion of that A and B, both events might happen at the same time. So how do we figure out the probability of either one of these two events happening? Well, you take the probability of event A happening by itself, add to it the probability of event B happening by itself. But if you just added those two together, well, then you have the spot that's in both A and B, the intersection, the overlap. You'd be counting that twice if you just added those two together. So what you need to do at the end is subtract out the probability of both events happening in here, and you get the overall probability of one event or the other, the union of the two, happening. So let's put it into an actual case. We have Anthony, and he has a 75% chance of getting an A in stats and a 55% chance of getting an A in managerial economics. This is his subjective forecasting of his chance of getting an A in both of those courses. He also believes that he has a 40% chance of getting an A in both of the classes. So what is the probability that he gets an A in at least one of these classes, and what is the probability that he's not getting an A in either of these classes? Well, we can solve the first, and that complement rule is going to help us solve the second. Let's start in the beginning. What is the probability that he gets an A in either statistics or managerial economics? Well, we've already determined that he has a 75% chance, according to his estimates, of getting an A in stats. He's pretty good at math. He thinks he has a 55% chance of getting an A in managerial economics, less confident in that class, and he thinks there's a 40% chance that he'll get an A in both. Well, we can apply this addition rule down here to figure out what his probability is overall of getting an A in either class. Take the 75% chance of getting an A in stats, the 55% chance of getting a in managerial economics. If you added those two together, a little quick math tells me that's a 130% chance. That can't be. You can't have more than a 100% chance of something happening. And that's because we are double counting that 40% chance that he thinks he'll get an A in both. So we subtract that out. 75 plus 55 minus 40 gives us 90. Anthony has a 90% chance of getting an A in either one of these courses. Well, what's his chance of not getting an A in either of those courses? That's a big, scary looking formula right there. Don't overthink it. If there's a 90% chance that he gets an A in either one of the courses, well, by that complement rule, we determine that there's only a 10% chance that he doesn't get an A in either course, because either he's going to get an A in one of them or he's not. There are only two possible outcomes. Some events are mutually exclusive. Both can happen. That wasn't the case with Anthony on the last slide. He can possibly get an A in stats or an A in managerial economics, and getting an A in one class does not preclude him from getting an A in the other class. But sometimes you will have outcomes where that's the case. Only one or the other can happen. Well, that's really easy because now you can't double count. There's no chance that both of them will happen. So this is a case where you can just add A and B together. So let's suppose that the probability that a recent business college graduate finds a suitable job is 80%. This is not conditional upon any other event happening. Like you find the job or you don't. There's nothing beforehand. But what if one of those graduates had previous work experience? This is what we call a conditional probability, which is what this little type line means right here. This means that A happening given that B had already happened. So in this case, B is our prior work experience. What's the probability of A finding a job if the student had already had work experience in the field? Well, now it's conditional on the occurrence of the other event happening. And looking at these two together right here, we can find the probability of getting a suitable job goes up by 10% if a student has prior work experience. If you have two events, A and B, each with a positive probability of occurring, how can you figure out the overall probability of this conditional probability that we're talking about? Well, if you're looking for the probability of A, given that B already happened, what you can do is you can find the probability of both A and B happening and then divide it by the probability of B, of the event that it's conditioned on. In this case, A is conditional on B already happening. And that will give you the probability of the both. Inversely, if we were looking for the other way around, B given A, the formula would look like this. So the thing that you're dividing by, the denominator in your fraction, if you will, is always the probability of the event which is conditional in the calculations that you're doing. So we have here an economist that's predicting there's a 60% chance that country A will perform poorly, will have a bad economic period. And there's a 25% chance that country B will also perform poorly. There's a 16% chance for the both of these that both countries will have a bad economic period, that they will perform poorly. Things are linked. We have like a global economy right here. So what is the probability that country A up here performs poorly given that country B has already performed poorly? We can apply that formula that we had before, this guy right here. Let A be the probability that country A performs poorly. B be the probability that country B performs poorly. We had both of those numbers here. 60% chance that A has a bad period, 25% chance that B has a bad period. And we've determined right here that we think in both of these that the chance of both countries having a poor economic period would be 16%. Well, now what I can do is I can take the probability that both countries have a poor economic period, 16%, and divide it by the probability of the performance of the country that is conditional for the other one. We're looking for what's the probability that A has a bad period given that B already had a bad period, that performed poorly. So I would divide by the probability of B, and 0.16 divided by 0.25 is 0.64. And what we're saying here is that while country A has a 60% chance of having a poor economic period, if country B also has a poor economic period, the chance of country A going into decline increases from 60% to 64%. And here, that gives us statistical proof right here that country A and country B exert influence on one another. When one country has a bad economic period, it leads to an increase in the chance that the other country will have a bad economic period. Country A was only at 60% by itself, jumped to 64% now that we know that country B is going to perform poorly. Instead of conditional probability, there's also a thing called joint probability, which is the probability of one event and the other event happening at the same time. We can find the joint probability is simply the product of the two different probabilities we're looking for. So in our example right here, we are a manager, and we believe that 14% of consumers will respond positively to our new social media campaign. Firstly, whoever designed this, we need to replace them, because if somebody's going through all the hassle of making a social media campaign and they think there's only going to be a 14% approval rate, I don't really know what we're doing, but for the sake of math, we'll go with this number. And then also, we believe that 24% of this 14% that respond positively will end up becoming loyal customers. So we're saying here that we have a very small subset that's going to like this. And the subset of those people that do enjoy our new social media campaign, a very small portion of that is going to end up becoming loyal customers. Well, what probability is there that if we run this social media campaign, any one person will become a loyal customer? Well, all you got to do is multiply the two probabilities together. The probability of a positive response is 14%. the probability that someone will have a positive response that's given and become a loyal customer over here is 24%. If you multiply those two together, you come up with 3.36% or 0.0336. So what we're saying right here is that if we run this social media campaign, there's only a slightly better than 3% chance that this campaign, any one customer that views it, will end up becoming a long-term customer for our company. Not a great number, but depends on what business you are. Like if you're going to the entire US and everybody's seeing this, 3% of the US population is a lot. If you are a local business trying to attract new customers, well, 3% is not a good number that you want to have. So the return itself is subjective. There's a lot of qualitative factors you have to come in, but here we definitely have some mathematical proof that our retention right here is going to be very low. Not a large portion of people that see this social media campaign are going to end up becoming loyal customers of our brand. So events can be independent of one another. They don't have to have one conditionally affect the other. And if that is the case, then probability stands pretty freely. But some events are also dependent on one another, which means that you have to have the occurrence of one event to happen for the other event to happen. You can tell this by doing some quick math right here. If the probability of both events happening is going to be exactly the same as the probability of one event happening, either of them, then they are independent of each other. So let's put it into context over here. Suppose that for a given year there's a 2% chance that a desktop computer crashes and a 6% chance that a laptop computer crashes. I could, just looking at this and thinking about it reasonably, there's no way these are dependent. Like if your laptop blows up, it doesn't increase the chance that your desktop's going to blow up. They're isolated incidents. That being said, some people run bad, as they say. There is a 0.12% chance that both computers are going to crash in the period. Can we determine right now, can we prove that these two events are independent of one another? They don't exert influence on the other one? Sure we can. What we're going to do is we're going to use that formula that we had before. The probability of D given L. In this case, the probability that your desktop crashes now that your laptop has already crashed. Well, we determined right here that the probability of both of these happening in one period was 0.12%, or in decimal form, looking a little something like this. Let's take the probability of the intersection of both events happening, and divide it by the probability of one event happening. So in this case, the given thing, our laptop's crashing first. We take that 0.0012 divided by 0.06, and we get 0.02, which just happens to be the same probability of your desktop crashing. So what this means right here is that the event of your laptop crashing, happening ahead of time has absolutely zero effect on the probability of your desktop crashing, because the probability of D given L, 0.02, is the exact probability of D by itself, 0.02. This is absolutely independent scenario that we have going on, proven in mathematics.